Hi, I'm Motonari Kambara. I'm going to talk about Relational Future Captioning Model for explaining likely collisions in daily tasks. Let me start with the background of this study. In our aging society, domestic service robots can be promising solutions for those who require support. This video shows a typical scene where the robot is placing an object. When the robot places a plate in the middle of the desk, there is a risk that it may collide with other objects, causing damage to the plate or the robot itself. Since it sometimes takes 1 month to repair a robot, we like to avoid such damage. Based on the background, we aim to generate natural language explanations of the potential risks. If the robot can explain the potential risks to the user based on the current situation, the user can pause the task and avoid the danger. Furthermore, being able to explain where the risks are in natural language improves the explainability of the model. These slides show related studies. Our study is highly related to studies on predicting future events and generating explanations based on the current situation. MAT is a video captioning model that uses past information to generate a statement of the current event. Video BAT is a large-scale pre-training model based on BAT. These methods model the current event and statements of it, and not events up to the present and statements of future events. Therefore, these methods perform insufficient in generating caption for future events. This will be shown later in the experimental results section. Generating statements of future events from current events has already been studied and proposed as a future captioning task. In this area, for example, future captioning for automated driving is being addressed. In the next slide, I will summarize the problem setting for this study. This slide shows the problem setting for this study. This study deals with the future captioning in everyday tasks. The video and text on the right show an example of the input and output for this task. The target of this task is to take clips up to time t as input and generate an explanation at time t plus k. A clip is a video clip of each event. For example, a cooking process. In the next slide, we are going to explain our proposed method. We propose the Relational Future Captioning Model for explaining likely collisions, RSCM, which extracts relationships among past events, predict future events based on them, and finally generates a statement of the event. The novelty is the introduction of the relational self-attention encoder to effectively extract relationships between events. In the next slide, I will explain the RSA encoder in detail. We introduce the RSA encoder to extract relationships between events. The structure of the RSA encoder is shown on the left. The main feature of the RSA encoder is that it uses relational self-attention as the attention mechanism, instead of using the attention mechanism in the transformer. The RSA is used in the RSA layer as shown in the figure. The structure of the RSA layer will be explained in detail in the following slides. First, the query, key, and value are obtained from the intermediate features input to the RSA layer using a linear transformation. As can be seen from these definitions, in RSA, source target attention is calculated. Next, a linear transformation of query is performed to obtain the basic kernel phi-p. We also obtain the relational kernel phi-h from query and key. Here, we compute the correlation between query and key. Therefore, it can be said that the computation synonymous with this computation is also performed in the transformer. On the other hand, the computation of this relational context phi-z implies self-correlation of values, which does not appear in the computation of source target attention in the transformer. This self-correlation of values is important. Past event series can be considered time series data. Computing set correlation for time series data is useful to see the relationship between the data. For this reason, RSA is effective in future captioning. Finally, RSFI is computed using this. The acquired RSA replaces DT in the input event series. It then processes it through the field-form network and layer normalization to obtain the output of the RSA layer. The output intermediate features are used as queries in the transformer decoder. In the next slide, I'll explain the loss function. This slide shows the loss function. As a loss function, we use the sum of these functions. The info NC loss function is the loss function used in CLIP. This loss is generally used to increase the similarity between elements in a positive sample. In this task, the positive samples are the CLIP at time t and the statement of the event at time t plus k. Therefore, we increase the similarity of these very features in order to generate the statement of the future event that is appropriate for the CLIP at time t. Specifically, for example, in the example below, cook them in a pot of water is an inappropriate statement since this is the statement of the events at time t. In the following slides, I will explain the dataset used in the experiments. We use two datasets related to everyday tasks in the experiments. The first is a ucook2 dataset. This dataset is a collection of videos about cooking. Each video is divided into clips for each cooking process. Each clip is annotated with the statement of the process. The second dataset is a villa caption dataset. We newly constructed this dataset. This is a dataset of videos collected on object placement tasks by domestic service robots. As in the example shown on the slide, each video shows a robot placing a plastic bottle or other household item on furniture in a simulation. Each video is annotated with a statement of what collisions occurred as a result of the placement. The dataset consists of a total of 1,000 samples with training, validation, and test sets of 800, 100, and 100 samples respectively. The next slide shows the experimental results. This slide shows the quantitative results on the UQ2 dataset. The graph shows the result of the baseline, each ablation condition, and the proposed method. Each ablation condition will be explained later. The results show that the proposed method outperforms the baseline on the blue, medial, and cider. This indicates that the proposed method is able to generate more appropriate statements than the baseline method on the UQ2 dataset. Next, we are going to show the qualitative results. This slide shows a successful case. In this case, the chicken is covered with flour and breadcrumbs at time t plus 1. The baseline method only describes this as a flour. On the other hand, the proposed method appropriately describes this as flour and breadcrumbs. This indicates that the proposed method is able to predict future events adequately. Next, this is a failure case. In this case, the chicken is placed on a plate and seasoned at time t plus 1. The baseline method described it as cut the chicken into small pieces, and this is clearly inappropriate. The proposed method described it as place the chicken pieces in a bowl. This is an appropriate statement of the event at time t, but not of the event at time t plus 1. This indicates that there is room for improvement in generating captions for appropriate time. In the next slides, we will show the results on the villa caption dataset. This is the quantitative results on the villa caption dataset. On the villa caption dataset, the proposed method outperforms the baseline method on all metrics. Next, we will show the qualitative results. This slide shows a successful case. In this case, the robot will collide with the camera in the center during object placement. The baseline method describes this as black teapot. This is inappropriate. On the other hand, the proposed method describes this camera appropriately. This is a failure case. In this case, the robot arm collides with the camera and the green can in the center. The baseline and proposed method inappropriately describe it as white bottle and teacup, respectively. Finally, we are going to explain the ablation studies. In the ablation study, we consider the two conditions without RSA and without transformer decoder. First, here the results on the U2 dataset. The graph showed the primary matrix CIDA score was the worst when the transformer decoder was removed. This indicates that source tight attention in the transformer decoder was effective. This slide shows the result on the Relational Captioning dataset. The graph showed that the CIDA score is the worst when RSA is removed. This indicates that RSA is effective in extracting relationships on the Relational Captioning dataset. This is summary. This study focuses on the future captioning in everyday tasks. The novelty of RSCN is that it has RSA as an attention mechanism. Experimental results show that the proposed method outperforms the baseline method on two datasets. That's all. Thank you.